Welcome to the last session of today before we have the party. I appreciate that you had found time to come here to the tent and listen to me talking about how to optimize XQuery and the XML usage in SQL Server 2005. Most of what I'm going to talk about actually will also apply to SQL Server 2008, and I will call out during the presentation a little bit where we might have additional things to consider. Before I introduce myself, I would like to point out that this is a 400-level session. It was unfortunately advertised as a 300-level session, but it's actually going to go into quite a low detail and assumes that you have a priori knowledge about XML and XQuery in SQL Server. My name is Michael Rees. I'm a principal program manager in the SQL Server Engine team. I have been with SQL Server for almost 9 years, basically doing XML in SQL Server 2000 and 2005, and still own the XML functionality in addition to some other features in SQL Server 2008. If you want to know more about what are the features that you can use to deal with XML in SQL Server, then I would recommend that you go and download the presentation that Bob Boschma gave in the previous section. And I've already asked, about half of you have seen his presentation, and I will try to build on top of it. There will be some overlap for some slides and for some aspects, so that people that have not seen Bob's presentation obviously will also have an understanding of what is going on. The presentation's main goal is to talk about how can you make sure that your XQueries and your XML usage makes the best use with respect to performance. There are obviously different aspects that you can look at that impact performance, so we will cover a wide variety of those throughout the presentation. At the beginning, the most important question that you have to ask yourself is, when are you going to use XML? And when are you going to use relational? We will talk about how should you design your XML to make use of the XML in a way that you have performance in mind. We have some general optimization aspects. We look at how to use the methods in the different methods that you have that is exposed on the XML data type to make efficient use of them in the context of XML processing. And then we also look at XQuery and the application of XML indices. And if we are having time at the end, we might also get to do some Q&A. So let's gear up and get ready and dive deep down into the ocean and see what we can learn. Bob already talked about XML scenarios today, so I'm not going to go into much detail about these scenarios. There are basically three major scenarios that XML is being used in the context of database systems. The first one is using XML as a data exchange format. You are transporting your data between loosely coupled systems in XML form. You publish your relational data into XML form, and you take XML and move it back into a relational system. A second scenario is that you use XML to store your data inside the database because they are documents like Office XML documents, XHTML, and other XML formats. In that case, keeping the XML together as a document is probably more important than shredding it apart. The third one is that XML can also serve as a data model, and as such, it has certain capabilities that the relational data model does not possess, such as the ability to represent semi-structured information. Semi-structured information meaning you have sparse properties that are only existing on certain instances, or the structure of your information is evolving very quickly over time, such that you really don't want to go and evolve your relational schema at the same pace. So you basically keep it in XML, where the flexibility of the model allows you to evolve the shape over time of an instance on an instance-by-instance basis. In all these cases, you not only want to transport the XML, but you also want to be able to store it in some way and query it. And in this talk, I will first talk a little bit about how we should think about storing the XML data. And then in the main part of the presentation, I will look at querying the data as well. So let's think about how we should approach storing XML data inside the database. The first question that we should ask ourselves is the data that I get in XML form XML data per se, or is it just relational data that somebody has encoded for transport purposes into XML form? If the answer to the question is that the data is really tabular relational data, it might be customer containing orders, but it's still relational, then we should probably take the data and shred it into relational form. This can be done with any one of the 5 or 6 shredding mechanisms that we provide you with on the mid-tier or on the server. If the data does not completely fit the relational model, the next question we should ask ourselves is the data semi-structured? Meaning, is it still data? I don't care about order. There is no mixed content, but it has lots of ragged properties that are sticking out on the side. If that's the case, then we should probably store the structured aspects of it, the properties that are common to all the instances relationally, and keep the properties that are specific for an instance, that are basically the really semi-structured aspect of the data, and store that in XML form. Now, if it's not relational and if it's not semi-structured, the next level of question is the data an XML document? Meaning, is order important? Does it have mixed content? Is it like an Office Word XML document, etc.? If the answer to that is yes, then obviously it is XML, and we should keep it as XML. Now, in both of these cases, the semi-structured part and the document part, we still have a next question to answer, which is, am I going to query into the data? If I'm going to query into the data or not query into the data, I actually might choose a different way of storing the data inside the database. Because if I don't query the data, the most efficient way of storing it is to put it into a var binary max column. Now, var binary max, why var binary max and not text? The answer is that var binary max does not care about the encoding that your XML is in. So you're not going to get code page incompatibilities between the database code page, be it Unicode if it's an nvarchar, or whatever default server code page you have, it's varchar, and the encoding that the XML document itself says it is. So if you just put it into var binary max, you're safe. Now, this is the recommendation. If you just put the XML document in and you never query into the document, then var binary max is the right way to store it. On the other hand, if you actually query into it, then the recommendation is to use XML for storing it. Because XML gives you a queryable model with a query language that you can actually do declarative queries over the content of your document and unlock the information that you have inside your document. Now, when you store it as XML, then depending on use cases, you might want to use an XML index, either a primary or secondary index. How many of you have used XML indexes so far? Okay, about probably a quarter. Now, also, if you query frequently the same properties inside your XML document, you might want to actually think about promoting those properties out of the XML and store them relational, and then just query them relationally. Because if you go and query them relationally, you have the advantage of having a much more efficient lookup of the properties. And here I would like to refer to Bob's presentation earlier today, where he was showing you how you can do this property promotion using computed persistent columns, for example. Now, sometimes you might not want to query into the XML document, but you want to search on it using full-text search capabilities. And you might want to query and search on it. In both of these cases, if you want to search within the XML, make use of a full-text indexing. SQL Server 2005 provides XML-aware full-text indexing in the sense that it will allow you to disregard the tags that are part of the document and only search on attribute values and element content values. Now, the last question that you should ask yourself is the XML that I'm getting and I want to store inside my database constrained by an XML schema? And if the answer is yes, then think about, do you want to enforce the constraint inside the database, have the overhead of actually having to do the validation every time you insert or change the document, but have additional benefits that I will show you in a couple of slides? Or do you want to do the enforcement on the mid-tier because the connection from the mid-tier to the server is controlled completely by you, and you can trust that the validation always gets performed on the mid-tier? So these are kind of the decision tree trade-offs that I recommend people to go through when they start designing systems where they get data in as XML. Now let's look at the architecture that SQL Server 2005 and 2008 supports with respect to XML. When an XML, oops, wrong button. When XML comes into the database, it gets parsed using an XML parser. The internal representation that the parser outputs gets stored in an internal binary format in what we call the XML data type. As Bob mentioned earlier today, the XML data type is basically a model of the XML that describes the nodes and attributes at the data level and not at a lexical level. And the binary XML is just a way for us to more efficiently represent that information. Now, if I have an optional schema associated with the XML data type, I can use that for doing validation. That validation will actually affect the internal representation by adding type annotations to it. Then I can use xquery to run on the XML data type. And I can do DML statements to do partial updates of my XML structures. Now, the xquery, as Bob also explained earlier today, is not running on the binary XML representation per se. What it actually does is it gets translated into a query that runs against that internal node table that gives a complete relational representation of the XML. Note that the binary XML that we have designed there for internal storage has been optimized to be efficiently translated into this node table format, more efficiently than the textual representation. Now, you don't want to have this node table created every time you query. So if you have lots of xqueries running against the XML data type, you persist it using a primary XML index. And since you want to have queries efficiently executed against this primary XML index, which is an internal table, you can define additional indices, which we call secondary XML indices, against the node table that further will give you cost-based optimizations against the xqueries that run against the node table. And we will see more examples of that later during the presentation. You can still use OpenXML and the nodes method to take XML and shred it into row sets, which is one of the shredding mechanisms I mentioned earlier. And you can take, for XML, to take your row set and create XML out of it. And Bob had a nice explanation of the different for XML modes that are available with SQL Server 2005. So having seen now what we can do, let's look at some of the individual aspects that impact performance of your system when you deal with XML. Let's first start with the general aspects that you have to look out for. Many of these aspects are actually not only respective to XML, but might, for example, also apply to if you deal with large object types like var binary max or nvarchar max. The first aspect is concurrency control. Currently, in SQL Server 2005 and 2008, when you operate on XML data, the row in which the XML data exists gets locked. In addition, if you have an XML index specified, the internal table acquires locks for all the rows that are affected by your query. Now, since a single row inside your primary table can have lots of rows inside the index, because there might be lots of nodes inside your XML document, and each row represents a node, you might get lots of locks on your primary XML index. Now, having lots of locks on a table can lead to lock escalation. What would that mean? Well, it means that you get a lock escalation on your primary XML index, which then locks the whole primary XML index, which means it locks more than just the documents that you have locked inside your primary table, which means you can actually get into situations where you get reduced concurrency. So the recommendation there is that you actually, for example, if that's something you encounter with, then you should use snapshot isolation in SQL Server 2005 to reduce the amount of lock conflicts with read locks. And then you only get lock conflicts if you do concurrent updates. Speaking of another aspect is transaction logs. Transaction logs have been seen to lead to, for example, being filled up if you do bulk insertion of XML documents into your XML indices, because there are lots and lots and lots of nodes getting inserted. There are lots and lots of rows that will be locked as part of the logging. So the recommendation there is that you delay the creation of the XML indexes until you actually have finished your bulk loading. And also another recommendation is, and that's valid for every use of a log, is that you put the log on a different disk than where you have your primary data. And finally, if you have lots of data that you're inserting, again, that's a general recommendation, pre-allocate your database file size instead of having it auto-grow, because that kind of gives you some performance improvement. XML, being a large object, up to 2 gigabytes per instance, has the same in-row, out-of-row behavior as it has for large varchars and var binaries. In addition, you yourself can decide to move XML out of the table and put it into a side table as part of your data model design. In each of those two cases, if you have it out of row, it gives you additional performance improvements on your purely relational queries if you have relational data combined with the XML data. That way, you would not have to scan, for example, the XML inside the table that is still stored in row if it's small enough. Also, one aspect is the node table is clustered based on the primary key and the node ID that is being generated for each node. Now, that clustering can lead to nonlinear insertion times if you are inserting new objects into an XML data type instance. So the recommendation here is that you are using some identity column that has automatic growing of numbers so that you actually have append-only behavior during your insertion instead as a primary key, instead of having some semantical key that has potentially impact on the ordering. So this was a couple of the general recommendations. Now let's look at what should we do when we model XML data. Because depending on what we model, we might have impact on the performance as well. Now sometimes we don't have a choice. Maybe the model and the XML format has been defined by an industry consortium. We can't go and change that. But maybe it's me and my developer in another department that has the freedom of deciding what XML format we want to choose for storage. In that case, there are a couple of aspects I normally point out. One is, if you want to store your data element-centric or attribute-centric, which one is better? That's a frequently asked question I hear from my customers. And the answer on that is always, it depends. It depends upon what type of data you want to model. If you have complex properties, etc., then element-centric is basically the only way to go. On the other hand, if it's just about performance, then the recommendation is that attribute-centric normally gives you smaller data sizes, more performant query access, etc. We had one larger insurance company recently in our labs that was doing some tests also between attribute-centric versus element-centric, and they showed across the board a size improvement and performance improvement around 20 to 30% just using attribute-centric data. However, attribute-centric data has certain limitations. It cannot contain complex properties, and it cannot be repeated, so you can only have a single one, which also has an impact on performance because the parsing actually is more expensive, especially if you have lots of attributes, certainly, then the uniqueness check during the parsing might become more expensive than just checking through the elements. The next point is a pet peeve of mine. How should I model XML? I see lots of people that come up with the second example there. Entity type equals customer. Property type equals name containing a value. This is not what XML was designed for. XML was designed for giving you the power of putting the names into the tags, making the names part of the structure. So instead of using that meta description, please use customer, name, value. That way, you not only have specific names giving you shorter path expressions, but the queries actually can make use of that information as part of your path expression processing. And you don't have to do dynamic lookups of values to figure out whether it's a customer or whether it's a name, etc. So the queries become much shorter and more efficient to execute. The last one is kind of a trade-off. It doesn't necessarily have lots of impact on your performance unless you overdo it, which is putting wrapper elements around collections. If you have hundreds of orders, some people then always put an orders element around it without any additional information. That has the problem that you're actually going to add additional elements to your document, which increases the size of your index in your document, and the path expressions are getting longer. Now, the last part with the way that we process path expressions actually is not going to be such a big performance impact, but it adds up to the data that you have to store and index. And if I say /customer/order, I'm already getting back all the orders. So why do I have to have that additional orders wrapper around it? It only makes sense if either it's mandated by an external schema or if you put additional properties on that wrapper element. So the next one is, should I use an XML schema collection if I have schemas that constrain the data? If I have no schema on the XML data type, we call that untyped XML. You can still use XQuery on it. You can still define indices on it. So you're not losing any functionality on that part. However, the semantics is different. Atomic values are always untyped, weakly typed strings. There is no schema validation overhead, which is good from a performance point of view. And there are no schema evolution revalidation costs or having to drop a schema and add a schema if your data changes, etc. So there are some advantages of not using the schema and doing validation on the mid-tier. On the other hand, a schema can also be positive because it gives you structural information. If I have an atomic typed element, for example, when I store it inside when I index it, I now only have one row in the index instead of two rows in the index. Static typing can detect cardinality issues and feasibilities of expression that I couldn't do before. I cannot add a date with a number, and it will tell me during compile time. XML schema also provides me semantic information that I can exploit during optimizations. So if the elements and attributes have the correct type for comparison, then I don't have to do runtime costs, which will improve the performance of my query. And I can potentially use my index to actually do a lookup, which I cannot do otherwise, and we'll see examples of that. So let me quickly go over the methods that we are having on the XML data type. We have a query method that takes an query expression and results in another XML instance, always untyped. The exist method returns 1 if the query expression returns at least one item, 0 otherwise, or null if the input was null. The value method extracts the value of an query expression and casts it to the specified relational type. There are some restrictions on that, and I jump over those. And finally, the nodes method, which is kind of a way for us to give us back an XML data type for every node that has been specified in form of a row set. And then I can do one row at a time processing in the relational context. It appears as a table-valued function inside my query plan if there is no XML index specified on the data type. I also have the ability to refer to relational values from within xquery using SQL column and SQL variable. And they refer to exactly what the name says. So SQL variable allows us to access SQL variables and parameters in the context of xquery. This is an example where I basically extract values out of my table where the ID of the B element is the same as the value that is tied to the SQL value variable. SQL column allows me to access other column values within my query expression. So in this case, I do a join between T and S, where I look up that the ID attribute of that same B element is equal to the value of the s.val column in the S table. There are certain restrictions in SQL Server 2005. Actually, in SQL Server 2008, one of the restrictions has been lifted. So that was enough talk. Let's switch over to demo a bit. Throughout the demo, I'm now going to show you some good, first some bad queries, and then some good queries. And I do that over a data set of 4 databases that contain the following information. First, I have a table that contains XML documents of this form here. So let me open this one. It's basically a customer containing some structural information about names, street, city, zip, etc. And it has orders within. And then it also contains nodes, which is a mixed markup type representation of some data that I store with the customer. I also have a table that contains contact information. The contact information is relational. It has a contact ID, which happens to correspond to the contact ID that I use inside my XML, and the phone number, which is not available in the XML context. In terms of cardinality, each one of the databases has 20,000 XML documents that I have artificially generated using a script, and it has, at the moment, only 4 contact phone numbers. Now let's look at what impact using XML has on the size. Sorry. This rather complex query here is looking at some DMVs and catalog views to find out how much space am I actually using for my XML data and my indices. So let's execute this. What I have is I have 4 databases. One database just contains untyped XML data of that form before without an index. One contains the same data with a primary key index specified. The third one contains a schema-constrained column version of that, where there's actually a schema constraining it. And then the fourth one is a primary key index on that table. So let's look at the impact that having these different representations have on the size. So you see here the first one, the query opt is the one without the primary key. And you basically see that we have about 15 megabytes of data. And note, this is running on an older laptop, so I couldn't like use gigabytes of data for this. The same, and this means this is the size that it is when it's untyped. The column down here, line number 5, is the index that is on this data set. Remember, Bob earlier said it's a factor of 2 to 5. It can actually be worse than 5, but we rarely see it worse than 5. In this case, it's a factor of 3 that the index actually uses in addition to the primary data that I have inside my table. Now, the interesting part is if I have type information, then my XML column will cost me more because I now have all the type annotations added to the data. And since I have lots of leaf values in my XML document, because it's a flat document in terms of hierarchy, it actually adds up quite a bit. If I would have more complex structures, it would actually be less bad. So I suddenly go up to 36 megabytes. Interestingly enough, the index on it is actually smaller. The reason why the index is smaller is that I have lots of element-centric representations. And if I have leaf values that are elements with simple types, I actually use less space in my index. So actually, my index is smaller. OK, so this is enough about the data that we are using. Now let's go and look at some of the queries. And I will do that by first showing information on the slide and then switch back to the queries. So one of the first things that I have seen people do is they need to get values out of the XML and put it into relational context. And what do? Is they write something like this. They say a cast of a query method that extracts some value out of the XML. That value gets cast to a string, and then I cast it to an integer. This is bad. That's why we have the value method. And that is going to be perform much faster. Another thing that I have seen is people saying node.query, and then the query is a query expression. In this case, it's just giving me back exactly the node on which it already is. And then I apply the value method. Well, why do I have to query and copy an additional XML instance? That's bad too. Just use the value method directly. So these are two things that I actually have seen people use in production and then complain about performance. And these were easy fixes. Let's see how that actually looks like if I run code on that. Let me connect to my unindexed, untyped database for a minute. And let's run the first example here. And while it's running, because it will take a while, let me explain what this is doing. So you see here there are a couple of casts there that do exactly what I have shown before. Mainly it is using the query method and then cast it to a string. And in one case, it also casts it then onto an integer. In addition, also, there are a couple of where I do a query with a dot value. And I'm using the nodes method there and a join with my contact info to actually get also the phone number out of that information. So this is a frequently encountered kind of shredding of relational data, of XML data into relational and adding some relational data to it. Now let's see how long that actually took. Oops. We see down here it's about 29 seconds. And if I would have turned on the set statistics time on, would have seen that it actually would have been around 30 seconds or so. Now let's do the same query, but instead of using these convoluted casts, just use the value method. Let's see what that does. It still will run for a while, and you have just seen the result, however, comes back a little bit quicker. And now I'm done after about 10 seconds. So a factor of 2. That's not bad. I can further improve this by having typed value. If I have a typed value, for example, let's connect to my typed instance, where I also have a primary XML index. I execute this query here. You notice that inside the value method now I don't have to say bracket 1 because my schema tells me there is exactly one first name and exactly one last name. If I execute this, it should also get returned in about 7 seconds or so. Let's see. Yeah. Another frequent problem that you see when you're using the methods is that people just put the methods in arbitrary orders inside the select clause. Now, there shouldn't be really a reason why this is important. However, we can actually aggregate these method invocations together and improve our performance by pushing multiple path expressions in. And our algebraizer at the moment only does that if they're actually coming next to each other inside the select clause. So there are certain restrictions on when we do that optimization, which are outlined here on the slides, which you can read for yourself. But let me quickly show you what this means. By the way, the singleton information restrictions, for example, that we have can be given like this. So let me go back to the code again. And let me show you what happens if I add orders and customers. So in this case, I'm extracting orders and customer information. And as you can see, I have 2 customers, followed by an order, followed by 2 customers, followed by an order, followed by 3 customers. And when I execute this query, it takes a while. It's still executing here. And you can also see that I still use several applies there with the notes method to actually get at my customer data and my orders data. So if I look now, it says here 25 seconds that it took. And if I go and look at the actual information here, you will see there's like exactly 25 seconds. Now let's do it differently. Let's group them together. Let's have all the customers together and all the orders together. And note, I have to have a primary index for this optimization to work. Let's see how long it takes here. It still will take a while. But I should be shaving off a couple of seconds from the execution. You see it ended in 17 seconds. So that's a quarter performance improvement, right, or a third performance improvement right there. Let's switch back to the slides. So as I mentioned, you have to have at least a primary XML index there for this optimization to work. Now, another thing that you might see is that you have join comparisons. You might want to use a join that you have seen previously in the demo was that I join my contact info. And there are 2 ways of doing the join. One way is to use the value method to extract the value into the relational context, do the comparison in the relational context. Or I can use my SQL column function and move the relational value into the XML context. Now, if you're using the exist method for doing, in one case, then you use the SQL column SQL variable. That is normally more efficient if you have a secondary XML index present. If you don't have a secondary XML index present, then using the value method to extract the value into the comparison relationally might be more efficient. That's a case where you have to do some experiments with the data that you have at hand. So if you have a secondary XML index present, then this is the bad way of writing it. You should not do the comparison using the value method. You should actually move the SQL column inside. Also, if you apply this on an XML variable or parameter, then the value method also is going to be still more performant because there are no indices available on variables or parameters. Another problem that you might encounter is that you write your query with an is null or a case statement. And I write the method twice. Well, it actually gets executed twice too. So the better way of writing is to actually use a subselect. So let's look at the code here, what it does in terms of performance. So in this case, what I do is basically checking if my value is null, then return null found, otherwise return the value. And do that for every node within my customers here. Now, when I execute this query, this will take a while because now every one of these methods gets executed twice, both for the check and for the else clause. Okay, it starts returning results. And now it's done, so let's see. It took 20 seconds, or almost 21 seconds. Now let's do the same by moving the value methods into a subselect and use the case outside. The result gets returned much quicker, and I'm actually done after 5 seconds. So that's not percentages, that's already factors of performance improvements. You should also do that with null if, which is another frequent case. Now let's use the slide. So this is kind of the optimizations that you can do with just looking at how you use your methods without looking into the xquery itself. Now let's look at how we can actually improve our xquery writing to make better use of the knowledge of how the xquery gets processed internally. In order to understand how that gets processed, let's look at how we actually process SQL and xquery expressions together. And Bob has shown the same slide during his presentation. So first, you take your select statement and you parse it in the SQL parser. You do your SQL type checking and you do the SQL algebraization. During the parsing, it will recognize these methods and will call out into an xquery parser that then will do the xquery parsing, the xquery static typing, and the xquery algebraization. The typing might use the XML schema collections to actually have additional information available about cardinalities and about the actual data types. Once you have these algebra trees, you basically combine them into a single algebra tree that you then statically do some optimizations with and map it into a physical operation tree, which then gets executed at runtime and might get further optimized by using available XML, relational, full text indices, etc. So let's look at some of the operations that we had to add in order to be able to support xqueries inside our query plan. Not every operation existed inside the relational engine. So the first one that we added was what we call the XML reader table valued function. This is the function that actually goes and takes the XML and creates our node table. It's used when there is no XML index present, or it's used to create the XML index. It actually allows us to push XPath expressions in. So if I have certain XPath expressions, I might only produce a subset of the node table that is relevant for the XPath that we pushed in. Multiple XPath filters can be pushed in to reduce the node table to a subtree, which is an optimization. However, since it's a table-valued function, our optimizer is very bad at doing a cost estimation for those. It's basically always 10,000 rows. If we push an XPath filter in, it does some adjustment of that. But even the adjustment might be way off because the initial value is way off. And this is a limitation that the SQL Server Optimizer cost estimation has at the moment, is that it simply does not know how to deal with table-valued function of any kind, the ones that we write or the ones that you guys write. This is the output format, simplified. Bob Sporsman's presentation has a much more detailed representation, but the details are not that relevant for our purpose. So what we are generating here is basically the node ID, which is a hierarchy ID that is like a Dewey Decimal numbering system that you might see on library books. We have a tag ID that kind of abstracts the tag name. We have whether it's an element or an attribute or a text node, etc. If you have type information added due to schemas, we'll give you that type ID as well. We give you a value, and we give you the HID. The HID is important for our path expression processing. The HID is the inverted path that leads to the corresponding node. So in this case, it is the title within sections within books. The representation itself is not textual, it's some binary representation, but it has the same behavior and same characteristics. And we actually have what's called a path tree statistics on that column. So we actually have very good understanding of what the selectivity is of a path expression over our XML documents. Now you might also understand why I was saying use the tag names, use the property names as tags, and don't use this generic entity and property modeling. Because in that case, these paths are all entities and properties, and you don't know anything about the value per se. And so you always have to do lots of expensive joins. In this case, if I know customer name, I find the customer name using an HID lookup there. Other algebration operators that we added are so-called UDXs, or user-defined functions. One is a serializer that takes the query result and returns it as XML. Another one is the string UDX. It basically evaluates the xQuery string function, which is aggregating all the text nodes underneath an element into a single text string. The data UDX evaluates the xQuery data function. The data function, in some cases, and we will see that later, might revert to be actually be transformed into a string UDX. There's a check UDX that is doing validation if I insert XML or update XML. And the actual UDX name is visible inside the SQL Server Management Studio property window. So you see it there. In the show plan itself, it just says UDX. So what are the optimal uses of xQuery? The first thing is xQuery always does atomization. What is atomization? Atomization is I take a value of a node, and instead of taking the node, I extract its value. So if I say customer where name equals John Doe, then the name is a node. So in order to be able to compare it to the string, I have to extract the value of that node, and that's called atomization. Value comparisons, xQuery casts, the value method itself, all require atomizations of nodes if you provide a node. So in this case, if I say age equals 42, it's actually data of age equals 42. If I say an atomic typed element age equals 42, it's the same, data of age equals 42. However, if I have untyped XML, and I say person age equals 42, then this actually adds the UDX string of age equals 42. If I have, however, a text node in that later case, then I say age/text, then it's again only atomizing the text node, and it does not add the UDX. Understanding this means that if I know whether I have a schema, if I know if I have leaf attribute or elements, I can actually rewrite my query to avoid that UDX. Either I add a schema or I use the /text to get there. Why is that important? The UDX is an aggregator that does bad things at runtime, which makes it impossible to use the value lookup on the index, because it actually has to apply that transformation first. So avoiding that means that I can actually more likely make use of my index. Let me give you an example here quickly. Let's use an untyped database with a primary key. And let's turn show plan on for a second. This is again the query that does this join here. And it has lots of value method invocations with first name bracket 1. Each one of these value method invocations will do an atomization, which means it will insert UDX into the query plan. So let's look at the execution plan here. Let's just scroll down here. And you will see that each one of these plan strings here has an XML UDX, which then says name equals query data. And this UDX is actually the string UDX that gets executed and inserted every time. And since that gets executed, I can't make use of any index value lookup. Let's look at the time that it took to execute the query. See, it's about 15 seconds. Let's see what happens if I run this query where I, instead of extracting the name, I extract the text node of the name. Oops. Now this is executing basically the same data, gets the same data out. And in this case, it does not give us that much performance improvement because there's lots of other stuff that costs in the query. But if I look at the plan, you will notice that the UDXs are gone. Instead, there's a top, which is much cheaper in terms of implementation. And the execution time was 12.5 seconds. So we saved 2.5 seconds of the query by doing that. Another thing that you have to consider is when you do comparisons between values, that you are avoiding costs. How many of you know about that in the SQL context? A few, good. Because in SQL, you have lots of implicit costs happening. And if you don't know what types you're comparing, you might actually get these costs inserted, which have the same impact. No index gets used, performance suffers. Same here. So, for example, if you have an untyped attribute in XML, no schema associated with it, and I say person age equals 42, and I provide the 42 as a numeric literal, then the algebraizer actually inserts this decimal cost to it. And that's costs additionally. In untyped text node, the same thing. However, and also if I, for example, have a typed node, salary, that says I'm an excess integer, but I go and compare it with a double, it gets implicitly cast to a double. So the important aspect here is that you should avoid these implicit casts if you care about performance. So what do? Well, you use the appropriate type for comparison. So for example, in the first two cases where you have untyped data, you compare against the string. Untyped data is basically like the SQL string type. It's weakly typed, can be automatically promoted to all kinds of other types. Or you use a schema to declare the type if you really need to have numeric comparison, for example. So let's look at some real-life examples. In this query, I get myself all the documents where the year is equal to 2000. Note that I'm running this on an untyped database. So if I execute the query here, let me get rid of the execution plan here because that often has a little bit of an impact on how efficient the query actually is. Let's look at the time that it takes to execute this. So this was about 0.6 seconds. Now let's do the same, but let's compare it against 2000 as a string literal. Note, this is an untyped document. Say that again. And now the result is 400 milliseconds. So I saved a third of the time. Note again that obviously if you do greater than, you probably want to have numeric comparisons because the ordering of numbers and strings is different. So the next thing is a couple of tips also about your path expressions. If you have the ability to write a single path instead of a long, extensive path with lots of predicates on it, you should avoid predicates in the middle of the path expressions if possible. Sometimes you can't because that's the semantics of the query, but you might want to look at ways of rewriting it. So for example, this is a way where you have predicates in the middle of your path expressions. You might want to rewrite that into a query that basically splits the path expressions apart. Now, the data set I have, unfortunately, does not show any performance improvements doing that, so I'm not showing you an example, but for some data sets, this can lead to performance improvements as well. Another thing is that you might want to move the ordinals that you have inside your path expressions towards the end of your path. However, you have to make sure that you get the same semantics. So if you have /A first one, /B first one, you could rewrite it as /A/B first one if the semantics is the same. It might not be the same. And never forget to put the parentheses around your path. If you forget that, that gives you a completely different semantics again. And it's better to write the bracket 1 around the whole path expression, because then the path expression can be moved into, for example, the XML TVF reader as a single path, then putting it in front of your attribute. So let me show you an example here as well. This time I show you actually the difference in semantics. In this database, I have one additional row that contains a document with two customers. The first customer does not have a zip code. The second customer has a zip code. Now this query gets me all the customers where I have a zip code with the value of 10,000. And it will show me both the expression where I have a predicate, a positional ordinal 1 on each step, and one where I move it at the end and apply it to the whole path expression. And there is a semantic difference in the example document that we just have added, which is that in the first case, where I say, give me the first documents, first customers, first zip, there is none. So I get back null. In the second case, what I say is, give me all the zip codes out of my customers into documents and take the first one out of that sequence. And that's different because it just takes the second one is the first one. The second customer zip code is the first zip code that gets returned, and so it takes that. So there's a semantical difference. So you have to be very aware of that when you apply that optimization. One of the things Bob's already mentioned is that if you have an exist method used, you want to straighten, maximize the XPath expression inside the exist clause. You can do that because in the exist clause, all you're checking for is existence of a node. You don't care which node it actually is. So instead of writing /book/subject text equals security, you say /book/subject /text, where the text node, or myself, using DAT, is equal security. Even more important is that optimization if you have conjunction inside your predicate. So for example, if you say, find me all the books where the price is between a certain range, then instead of writing it like this, it's better to write it as, give me the price where a price exists that is within the range. So let's look at an impact on an actual query. So the first one is now using the year inside the predicate. And I see that I have about a second. Now let's move it outside. And now I have half my query time. Another thing Bob mentioned is that you want to avoid parent access. Many people use the parent access because it's very convenient. And we had huge performance problems with the parent access in SQL Server 2000 in OpenXML up to SP4, where we fixed it. Unfortunately, it was a different development team that did the parent access in the xQuery implementation, and so they also screwed it up. So what we want to do here is basically we want to avoid that. So what we do is we do forward chaining, what I call it. We basically go first only to the customers in this example, and then we do another cross apply to get to the orders. Gives us semantically the same behavior, but it actually avoids the parent access impact. And I'm not going to show that in the demo, unfortunately, so that we can get to the indexing. Other things that we have to look out for is we should avoid the use of // if possible, and descendant accesses in the middle of path expressions if the data structure is known. Many people just say /customer / something, simply because they are too lazy to type out the path expression. It actually gives us more efficient performance. We can still use the HID on, with the // but it's going to be less efficient. Another thing is, if you do construction of results, use the xQuery constructor, or should you use for XML? And unfortunately, for XML is more efficient. So instead of writing your xQuery construction here, you should use for XML path to do your construction. That's normally more efficient than using the xQuery construction syntax. Now another thing that is about xQuery without using secondary indices. Now for XML has a new type directive in SQL Server 2005. That type directive creates automatic XML data type instances. So we should not do the following. I declare a variable as XML. I say set at x equals select from customers for XML something or other without the type directive. Why is that a bad idea? Well, the for XML result without the type directive gives us back a string result. When I assign that string result to my XML variable, it does a parsing of that string result and creates the XML data type. If I use the type directive, what happens is that it takes the XML and creates the XML, and it's right there. You don't have to do anything anymore. So there's a certain performance improvement on that. So let me quickly show you that impact as well. So here I'm actually jumping over to my Northwind database. And I execute these two statements. Exactly the same. I get my orders back in an XML form, one with and one without the type. First, you see, takes about 181 milliseconds. The second one takes 23 milliseconds. So an order of magnitude faster by not having to do the reparsing. Also, some people are wondering, should I use for XML path or should I use for XML explicit? Both of them can do more or less the same thing. The recommendation is to use for XML path if you have complex groupings for additional hierarchy levels and other things instead of using for XML explicit. For XML explicit, might still be more efficient than for XML path, but way harder to maintain and write. If you have complex nestings, if you have lots of like nesting levels that you have to create, because of the way that for XML explicit just creates this huge table and then you create XML all one at a time, while for XML path you compose XML documents that you then compose within other XML documents, and that means lots of data movement which might impact your performance. But I still recommend that you go with your for XML path first, and only if the performance does not satisfy your requirements, look at the explicit mode. Okay, let's go to the last topic, XML indices. XML indices, we have primary indexes, we have secondary indices. One of the things that you have to watch out for is the primary XML index always will be created single-threaded. That's because SQL Server 2005 and 2008 cannot do parallel index creation on indices that include lob types, and the primary XML index does that. So this is a restriction that we inherit from the system. However, secondary XML indices, since they're normal non-clustered indices, they actually can be done in parallel. If you define an index, the primary XML index will always be used if you have defined it. It's actually algebraized, which means that it's not a cost-based decision. Secondary indices are cost-based decisions. So the optimizer will use them depending on cost information. If you do maintenance, primary and secondary indices will always be maintained efficiently by only updating the changes of the subtree that actually has changed. However, there is no online index rebuild, again because of lob type inferences, the same restrictions we also have in 2008 for spatial indices. And as I already mentioned, if I have a cluster key, that might lead to nonlinear behavior. If I have a schema associated with my column, I will still have to revalidate the whole instance. So I will have to touch the whole instance, which means that if you have a schema associated with it and you do updates, you have to be really thinking about what type of updates you actually want to allow. So let's look at an example. If I take this simple XML document, a book with an ISBN attribute, section, title, some mixed content there, and do an index on it. How does that look like? So this is the index structure. Again, a little bit simplified. The first column, the PK column, is the primary key that points back to my original relational table. The XID is my node ID. That is using that Dewey Decimal encoding, or what we now call hierarchy ID in the context of SQL Server 2008. Then we have the actual tag node information. Most of that is not actual values. These are tokenized information. So we have the tag ID saying what is the ID of the token. So we have book ISBN. You will see here that section has the same tag ID on different nodes. We say whether it's an element, an attribute, a text, which is an enumeration. And then we have the type ID, assuming that we have a typed document, which I assume in this context we have. Then we have the value for the nodes that have values, which is attributes, text nodes, and elements. We can see here, for example, that the text node there has a value called nobody, with the value nobody loves that box. The reason why this is a text node is, and not folded up into the section element, is because the section element is not typed as an atomic type. It's a complex type, so it has to keep its own node. On the other hand, the title element is typed in the schema as a string, so we actually fold the text node up. That's why at the beginning of the presentation, you have seen that the index actually gets smaller if you have a schema with such simple typed elements associated with it. The last column, again, is the HID. So you see, basically, this is almost the same schema that the table valued function generates for the node table, except for that we have the primary key associated with it. So now if we create the primary key, and we create our non-clustered secondary indices, the value index basically takes the value column and the HID and the primary key and can very easily answer queries about values or values and paths. The property index takes the primary key as first, HID, value, and the node ID. And it basically allows us to very easily answer queries where I already know the row due to other means. And the last one is the path index, which allows me to, given a path, identify what value and what node I might have and what row I belong to. So let me quickly switch over to the last part of the demo, where I use secondary indices. Let's rerun this query again here that basically extracts some information out. Oops, I need to go and reconnect to my database, of course. So this again does a join between my customers and my contact info to get all the information out. I'm here running on a typed database with a primary key present. So I'm done after 12 seconds. I also have here a query where I basically do that check about the year range. Let's just for illustration purposes add the show plan here. So here the result time was half a second, as you remember. If I would have written it differently, it would have been a second. And if I look at the plan, you see that the plan is doing clustered index seek on my primary XML index. Now let's go and add the path index to my table. It will take a couple of seconds. Okay. Now let's rerun. Let's first rerun the first query. Remember, that took 12 seconds. Hmm. 8 seconds. So remember that originally this query was running for over 20 seconds, and now we are down to 8 seconds, just using secondary, primary index and secondary indices. Now, if I look at the query plan here, you will see that now I have somewhere down there. I still do a primary XML index lookup here. But in some cases, like here, for example, where I do my join, I actually now look at the secondary XML indexes. And the reason why I'm able to do that is because I use the SQL column here. And this gives me a better performance than if I would do the value method where I promote the value out, and then I do the value comparison outside in the relational context. And at that point in time, there is no relationship of the value back to the index anymore. And so the query processor will not be able to use the secondary XML index for that lookup if I use the value method. However, if I use the exist method with referring to the value using SQL column, then I can do the lookup inside my XML index. Now, just show you the simpler query here. Remember, it was originally a second, and now it's 5 times faster using this, this index. And again, if I look at the execution plan, now instead of using only the primary index, I'm actually using the path index up here now for answering my query. And if you look at the operations down there, you actually see that the path and the value lookup are both being pushed into the index lookup, so I actually don't have to have an additional filter step. Okay, now just to show you another cool trick, since we have 1 second left, you sometimes can use your full text index also to do some performance improvements if you do string contains queries. Now note, full text contains is not the same as the xquery contains. Xquery contains is looking exactly at the value as is, byte by byte. It does not do any stemming or anything like that like full text indexing does. But since full text indexing gives you kind of a primary filter that gives you all the values that you're looking for plus some more, you can use it to narrow down the set of values that you actually have to apply your xquery expression to. So if I, for example, want to find all the documents that contain snoozes inside the notes, it takes a while. 4 seconds here. Almost. Now, I happen to have a full text index created earlier on this column. And so what I will say now is, I will add this to the predicates. I will say, find me all the documents that contain snoozes anywhere within the XML. And then I run the other expression still on it to make sure I only actually get those that are contained in notes and have the right string semantics. Now, this was returned in 140 milliseconds. That's quite a bit of a performance improvement. So with this extreme example at the end, I thank you very much for your attention. I hope that you learned something about how to use XML and xquery inside SQL Server for improving your performance. And I appreciate that you waited that long and wish you lots of fun at the party tonight. Thank you very much. And I'm available for first, I'm available for questions. And by the end of TechEd, the scripts will be uploaded on the website where you can also download the presentation.